Imagine you have a toy car on a straight track. Let's call the starting point 0, your home. If you drive to the right, you are going in the positive direction. If you throw it in reverse and drive to the left, you are going in the negative direction. Look at this top-down view of our road. If you drive to +5, an odometer pops up, counting 5 steps. Now, if you start over and drive backward to -5, the odometer still reads exactly 5 steps. In math, we call this absolute value. It is a step counter that tracks how far you traveled from home, regardless of direction. Because it only measures distance, driving 4 steps forward or 4 steps backward creates the exact same result. The absolute value of 4 is equal to the absolute value of -4. The lengths of the trips are identical. Try putting the car in reverse as far as you want. You cannot walk negative steps in real life. You are simply taking positive steps in a negative direction. Because of this, absolute value is always greater than or equal to 0. Later in calculus, you will track things like the movement of a planet or the acceleration of a car. These calculations rely on the fact that while directions can change, the physical distance covered is a positive measurement. If we know a car has driven a maximum of 6 steps from 0, we know exactly where it must be. It is trapped somewhere between the farthest it could go backward, -6, and the farthest it could go forward, +6. We can use this to build a specific boundary. If we say the car's distance is strictly less than 3, we draw dotted lines at -3 and +3. The car can get close to the boundary, but it can't touch it. But if the rule is less than or equal to 3, those boundaries become solid brick walls. Now touching the fence is allowed. These bounded zones create a neighborhood around our starting point. Calculus uses these exact zones to define how close one number needs to be to another for a calculation to be accurate. We can move home anywhere on the line. Let's place a friend's house at position 5. To measure how far another car is from this new spot, we subtract them. The absolute value of x minus 5 tells us the distance to that new house. If a car is at 3, the math shows it is exactly 2 units away. There is a common trap here. If you see the absolute value of x plus 4, it actually means the distance to -4. That is because adding 4 is the same as subtracting a -4. The target point has simply moved to the negative side of the road. On the top, you drive straight to your friend's house. On the bottom, you take a detour to a shop. The direct route is always shorter than or equal to the total distance of the detour. This is the triangle inequality. This rule allows mathematicians to set a strict ceiling on a total distance, even when the individual legs are changing. It ensures that a combination of small fluctuations cannot add up to something larger than a known limit. Absolute value also works with multiplication. You can find the distance of 2 numbers individually and then multiply them, or multiply them first and then find the distance. The result is the same, a positive value. The same applies to division. Slicing a road into 4 segments, or measuring the pieces first and then slicing them, gives you the same length. The distance remains consistent as long as you never divide by 0. If you square a negative number, like -3, it becomes a +9. If you then take the square root of that 9, the result is a +3. This process strips away the negative sign, effectively giving you the absolute value of the original number. This keeps equations predictable. By ensuring a value stays positive when it comes out of a square root, calculus can accurately find the slope or the rate of change for curves that dip into negative territory. If we zoom out, we see that our road is a continuous number line stretching forever. Every point is occupied, not just by whole numbers, but by every possible fraction and decimal in between. We use coordinates to mark these spots. A coordinate is the exact numerical address of a point. If we label a specific location as P and place it at 5, the name P is just a label. The number 5 is the physical address on the map. Having an address for every point ensures the road has no gaps. Calculus relies on this completeness to track movement. Without a continuous path, you couldn't accurately calculate the exact speed of an object at a single moment in time. To find the distance between any 2 houses, you subtract their addresses and take the absolute value.
By calculating the absolute value of 4 minus -3, we find a physical distance of 7 units. If we want to know which way we are traveling, we use directed distance by removing the absolute value. Pointing from 2 to 7 gives a positive 5, meaning we moved forward.
Pointing from 7 back to 2 gives a -5, indicating we reversed. You can find the exact center between 2 points by taking their average. Adding -4 and +6, then dividing by 2 gives you 1. This midpoint is the perfect middle ground between the two locations. These tools let calculus chop a complex area into perfectly defined sections, making it possible to calculate the total area under a curve. We can also describe entire sections of the road using intervals. Solid dots represent closed intervals, meaning the endpoints are included. Hollow dots represent open intervals, where the boundary is not part of the set. An inequality like the absolute value of x minus 7 is less than or equal to 4 defines a specific region. You start at 7 and move 4 units in both directions. This illuminates a safe zone stretching from 3 to 11. This is the foundation for the definition of a limit. By shrinking that allowable distance, changing that 4 to a 1, then a 0.1, and even smaller, mathematicians can precisely describe what happens as one number gets closer and closer to another. This language of closeness is what makes the rest of calculus possible.